Okay, we are going to do a video that's going to go over geometry of molecules. So what you're going to need the paper that you see on the screen right here that's got a summary of all of the different shapes. You're going to need a shapes of molecules model set that you can find in the classroom. You're going to need that for this video. You also need to get your notes out that say molecular geometry. Okay, so you need all of those things. So if you need to pause this video, go ahead and do that, and then we're going to go ahead and get started. Okay, so I'm going to essentially go through all of the shapes and have you build them with these kits that will help you understand and see what molecular geometry looks like. Forgive the headset, but in order for you to hear me, I had to wear it. So anyway, molecular geometry is essentially the 3D shape of what molecules look like in space. So you've got this VSEPR theory, which essentially talks about the valence shell electron pair repulsion theory and why geometry sets up the way it does. Electron pairs essentially orient themselves in order to minimize the repulsive forces. They like to get as far apart from each other as possible. And this is just an example of that. There's two types of electron pairs. There are bonding pairs that will form bonds. So you'll see me use these for bonding pairs. They're going to be these kind of little gray things. That's going to be our bonding groups. And then we also have what are called lone pairs. Lone pairs are non-bonding electrons that are going to be these little beige thingies right here. And you will see when we draw Lewis structures, these are the extra dots that we draw around central atoms that are not bonded to anything. So lone pairs will always repair more strongly than bonding pairs. So these, to repel, are going to maximize the distance between each other. So lone pairs will reduce the bond angle between atoms. The bond angle, as illustrated here, is going to be just like if you had a protractor, if you could measure the angle between the bonds of two atoms. Okay? All right, so for molecular shape, the first thing you're going to do is draw the Lewis diagram. You're then going to tally up the electron pairs on the central atom. Double and triple bonds for geometry only count as one pair. Even though they may have a double or a triple bond, it's only going to count as one pair for the geometry. And the shape is essentially determined by the number of bonding pairs and the number of lone pairs. So you'll notice on this little chart that that's how it's set up, right? You've got the total number of bonding groups, the number of lone pairs, and then the number of bonding groups, and then that will give you the shape and the geometry. So we're just going to run through all of these, and like I said, essentially we need to know these, so it's going to be important. First thing you're going to do is draw the Lewis diagram. Next thing you're going to do, we talked about this, tally those up. And we need to know those 8 common shapes and their bond angles. That's going to be really important to be successful. So grab your little molecules, and we're going to go ahead and get started. Okay, the first one that we need is going to be a silver one. This is going to be a situation that you've got 2 bonds coming off of the central atom. So I'm going to go ahead and grab the silver one, has 2 holes on it, and I'm going to use these little white ones, typically represent hydrogens. Okay, and you know, this one, we've got one that's only got 2 bonding groups. So when we put this together, you've got 2 bonding groups, no lone pairs. So 3D wise, it's going to look like this. This is the structure you want to build. If you need to pause as we're going through, feel free. And this is going to be linear with a bond angle of, let me get this in, there you go, of 180 degrees. So if we had our little protractor, here would be our bond angle of 180 degrees. And all diatomic molecules will always be linear. So any molecule that only has 2 atoms will always be linear. And this is an example right here of BeH2. Okay, so this central gray kind of metallic one is going to be a beryllium atom. Okay, next one we've got is when you have 3 total groups, 3 bonding, no lone pairs. So this time the one that you need is going to be the, let's see here, this little beige one right here. And again, we're going to put 3 bonding groups on the outside of that. So we're going to clip 1, we're going to clip 2, forgive me a little bit while it's taking me a minute to build them, and 3. Okay, so if we were to draw a Lewis structure, you'd have a central atom with 3 bonding groups coming off of the middle. And 3D wise, it's going to look like this. This is what's called trigonal planar is the name of the geometry. And the bond angle here is 120 degrees. That's going to be the distance between those bonds. Again, if you had a protractor, you could measure out that's 120. Example, this would be the, one boron with 3 fluorides attached to it. Okay, the next one that we've got is we still have 3 total, but instead of 3 bonding groups, we're going to remove one of those bonding groups, and this time we're going to attach a lone pair. Whoa! How's that for bloopers? Okay, let's try that again. So for a lone pair, you're going to have one of these on there. Okay, so the lone pair is kind of represented by this. This is a new kit. There we go. It's kind of represented by this beige, bubble. And again, we've got 2 bonding groups and 1 lone pair. This is going to be what's called bent. This will have a bond angle of a little less than 120. The kits don't totally illustrate this, but essentially when you put that lone pair up here, it's going to push this bond angle down just a little bit to make it a little bit less than 120. That's what we're going for on that one. This example, this would be sulfur dioxide, or SO2. Okay, next one we've got is 4 total, coming off of the middle, 4 bonding, no lone pair. So we need the little black one right here. Okay, this one is going to represent a carbon atom, and what we're going to do is we are going to attach 4 bonding groups around the outside of this carbon. Okay, so now when you draw this, and we're going to talk about 3D structures, how to draw these later, throwing things. This one is what's called 4 bonding groups, and you can see when we draw the Lewis structure, a lot of times this looks like a T, excuse me, but in reality, it's not. In 3D, it's not a T-shaped. What it is what's called tetrahedral. And tetrahedral, again, all of the bonds are as far apart from away from each other. So if we had a protractor and we could measure these would all be 109.5. Okay, 109.5. So again, you want to be building these molecules as we're going through here. And it doesn't matter which way we spin this, all of these bond angles would all be 109.5. Okay, and that's tetrahedral. Methane is an example of that. All right, the next one we've got is still 4 total, but instead of 4 bonding, we're going to take one of those bonding groups off of there, and we're going to go ahead and put back our lone pairs. Okay, so on my lone pairs here, get that built, put that right on top. Whoa. All right, so now I've got 1 lone pair and 3 bonding groups. And essentially what's going to happen is this is now going to be what's called trigonal pyramidal. And our bond angle was 109.5 when there were 4 bonding groups. Now our bond angle is, again, the kits don't show it, but these get a little bit closer and it goes down to 107. So that electron pair up here, the lone pair, repels these bonds just a little bit, forces them together, and we get all the way down to 107. Ammonia is an example of this. Okay, the next one we've got, still got 4 total things coming off of your molecule, but you're going to take off one of those, another bond. We're going to put another lone pair on there. So it would look like this from a 3D shape. Okay, so now we've got 2 bonding groups and 2 lone pairs. So essentially what that's going to look like, this is also called bent, even though we already had one that was called bent before. This is another one that's called bent. This bond angle is going to be 104.5. So we went from 109 when we had 4 bonding groups, 107 when we had 3. Now that we've got 2 lone pairs and 2 bonds, again, these are going to be pushed a little bit closer, and it's going to go all the way down to 104.5 is what this one would be. Okay, and that is going to be bent. Water is an example of a bent molecule, where in the central oxygen you have these 2 lone pairs that are kind of up to the top, and then these would be the 2 hydrogens attached to the water in the middle. Okay? All right, and again, I'm not doing a great job of using the right colors for the right atoms, but just trying to give you a basic background of the shapes right now. Okay, the next group that we get is going to be 5 groups coming off of the middle. So what you're going to need to find is the purple version. Okay, the purple version is going to represent a phosphorus. Should have 5 groups coming off of the middle. Get this one right. And we're going to build 5 bonds. 1, 2, 3, 4, and 5. There we go. All right, so what you can see is that you get these 5 bonds all coming off of the central atom. So you've got 5 groups. You know, you can kind of spin it in some different directions so you can see what it looks like 3D. But this is what's called trigonal bipyramidal. And essentially what happens is that if you look at this with one sticking straight up and one sticking straight down, you get 3 in the middle. So if you were to split this into kind of 2 halves and fill in all the sides, you'd have 2 pyramids kind of stacked on top of each other. I don't know. That's how it makes sense in my brain. But notice there's 2 bond angles here. If you're looking in this plane, with one sticking up and one going straight down, all of these would be 90-degree angles. Okay, so this one would be a 90-degree angle, this would be a 90-degree angle. All right, and again, you can see that with the 3D structure. The other angle is if you turn it this way and you get 3 bonds, you know, one of them kind of coming straight at you, you've also got these 3 in this plane. That bond angle is 120. Okay, so you get 90 here, 120 here. Okay, and phosphorus pentachloride would be an example of this one. Okay, last but not least, you've got 6 coming off of the middle, all bonding groups. So this time you're going to need to grab your yellow atom. This is going to be sulfur. So sulfur is in the 3rd, sulfur and phosphorus both, remember, are in the 3rd period or lower. So they can have what's called an expanded valence, meaning that they have more than 8 atoms in their outer shell. So it allows us to build some of these molecules and have some of the overlap. And I need one more. I got 5 and I've got 6. Whoa, I don't want to throw them. Runaway atoms. Okay, so I have my central atom that's got 6 bonds coming off of it. Again, they're all going to get as far apart from each other as possible. So this one is going to be octahedral. And you may be going, okay, well, 6 is not octa. Where does that come from? Well, again, if I were to fill in all the sides and kind of make this a cube, there would be 8 sides to this structure. So that's where the octahedral comes from. From a bond angle perspective, they're all 90 degrees. So if I'm in this plane, I've got 90 degrees. If I'm in this plane, I've got 90 degrees. Any conjoining bonds, no matter which way that I spin this lovely thing, are going to be 90 degrees. Okay, so, and again, sulfur hexafluoride, there's our 6 prefix, would be the example of a common molecule that would have this shape. So again, here's some examples how you would see this from the Lewis dot structure. You've got phosphorus trifluoride with a central phosphorus right here. We'll always do the geometry off of the central atom. So off of that central phosphorus, you have 4 total groups. 3 of them are bond groups, right? Because you have the 3 lines, 1 lone pair. So you just need to go to your chart, find the group that has, or the column rather, that has 3 bonding groups and 1 lone pair, and that's going to tell us that it's trigonal pyramidal. And then it has a bond angle of 107, which is what this slide is telling us anyway. Okay, so trigonal pyramidal, 107. Let me get my face out of the way here so we can try to read it. But you have it on your notes too. And this would be a 3D version. Again, we'll do drawing these 3D structures a little bit later. The next one here, you've got carbon dioxide. We're looking at the central carbon, the central atom. There are double bonds, but remember, for geometry, each bond only counts as 1 bonding group. So even though you have 2 double bonds, that only is going to count as 2 bonding groups coming off of the central atom, which is going to put it in a linear category and is going to make the bond angle 180 degrees. And again, there's just some different 3D representations. So as a reminder, we got to be familiar with that information on the attached chart. Hopefully that's helpful. For those of you that are kinesthetic learners, use these kits when you're practicing. It might really help with understanding what the 3D structure is as opposed to just the 2D Lewis structure. I hope that was helpful, and as always, please ask if you have any questions. Have a great day.